Is AI going to suck up all our electricity, or can we find a way to make it way more efficient? Hello and welcome to TechFirst. My name is John Koetsier. AI currently uses 1 to 2% of the planet's electricity. As it grows, it's projected to use almost 5% by 2030. And I'm not sure that the people who are looking at that know about all of OpenAI's plans and NVIDIA's plans and all those crazy plans to build massive, huge farm for AI. As it stands, we're looking at almost 945 terawatt hours per year just for AI. But there is a company that says it can shrink AI's energy consumption and its footprint by up to 95% without sacrificing performance. The company is Multiverse. We're chatting with CEO Samuel Mugel. Welcome, Samuel.
Hi, thanks, John.
Super pumped to have you. It's an interesting topic, super topical right now. I mean, we're just hearing all this news in the past couple of weeks about OpenAI building this and building that. I think Elon with Grok wants to build some massive factory for AI as well. You said you could fit AI models in a fly's brain or a chicken's brain. Talk about that. What's that mean? What's that look like?
So the usual way to measure the size of an AI model is the number of parameters, the number of trainable parameters. And roughly, you can equate that to the number of connections in a physical, in a biological brain. So we specialize in small language models. Therefore, we look at brains out AI models that have very, very few trainable parameters. And our smallest model is in the range, is under 100 million parameters. That's million with an M. If you consider that, if you compare that to the smallest, to the kind of smallest commonly available models like the Llama 3.1 and stuff, we're talking about models that have 1 to 3 billion parameters. So we're looking at something that's less than an order of magnitude less. In fact, it's so small that it equates roughly to the number of connections in the brain of 2 fruit flies. So we've named this model Superfly.
Kind of crazy. And yet it still works and works well. I mean, what do you lose when you shrink it down that much?
Yeah, it's still a very verbose model. So it's not our cleverest model. I do want to be upfront about that here. But it speaks very well and it retains a lot of knowledge and it's quite impressive. Like this is a model that's so small that it can run extremely fast. We're talking about like hundreds of tokens per second. I should probably double check that statement. So maybe we'll come back to that afterwards.
We'll come back to that. We'll add something on screen if you come up or your PR people come up with a different point there. Now, why do you want such a tiny one? Is that just like a proof of concept, or is there an actual business case for making a very small model like that?
There's definitely a business case for it. I think the point is that while it is fantastic to have access to models that are basically at the kind of Nobel laureate, like post PhD kind of level, are also use cases where you need to be able to interact with models that are very lightweight, very, very fast to do very simple tasks, like maybe control a washing machine or like control a home Alexa or to be able to run on the edge on your phone without relying on an internet connection and being able to control your whole data, you know?
Super interesting. So, I mean, currently right now, I think that in most cases, perhaps all cases, you're delivering your technology on AWS or in server farms, stuff like that. But you're saying basically this could be great edge AI. You want an appliance to be relatively smart. You know, you want to be able to talk to your washing machine or talk to your faucet or something like that. You know, give me water at 78 degrees or something like that, whatever, you'll be able to do that.
Yeah, precisely. For, like you so rightly pointed out, for Edge AI, there's applications everywhere, especially in our day-to-day lives. I left that part out, so thanks for the reminder. For the cloud, there's a ton of applications as well. Obviously, like everyone's getting super excited about agents. And the real shortcoming of agents is that suddenly you need to have an AI model that you're able
Mhm.
to call hundreds of thousands of times every time you run a
Mm.
program. And having an extremely lightweight model that's able to do like sanity checks or that's able to do sentiment analysis on like Twitter posts and stuff like that is extremely powerful for these agent applications.
It's super interesting. I had dinner in San Francisco recently with the CEO of an agent company, and he was telling me, it'll look for news that's relevant to you or updates or whatever, and it'll funnel it to you and all that stuff. And I'm going like, this has got to be orders of magnitude more compute and cost and energy use than what we had with like RSS or super simple like routing features that people were making 15 years ago, right? So we're putting a x 200x 1,000x the compute power to do something that's ultimately pretty simple. But if you can have just a little bit of intelligence there to understand just a little bit of what it needs to do, that's actually quite easy. That interesting. That's actually quite valuable. The second
Yeah,
thing that, go ahead.
You're you're absolutely correct. The scary thing is that I think that with AI compute use today, we're really only just scratching the surface. Like a lot of AI for the moment is still people running queries, or when you're running a
Hmm.
Google search, like you'll have an AI running in the background. But we still haven't really gotten into those applications of I run a program that's going to be calling thousands of like LLM runs a second and stuff like that.
Hmm.
That I think is really where we're going to see our AI, our cloud costs, our like GPU usage explode.
I was literally talking to a marketing tech company a week and a half ago, Braze, and they're applying LLMs to communications they're sending out to customers and stuff like that. But they have to limit it. They can't do it all the time. They can't spend whatever the compute is to make a complete, like human-like AI powered message in all cases. But if you have a smaller, very tailored model, that's interesting. The thing I was going to bring up that made me super excited, we were talking about edge AI, and we are talking about small LLMs and smart appliances and smart everything, is that one of my things is smart matter. I've been working on this, thinking about this, dreaming about this for better part of a decade, right? And that's ordinary things in our environment that have chips and radios and sensors and motors and can actually do smart, intelligent things. And now maybe with just a small chip and a little bit of compute and a very small model, they can actually do super crazy, cool, wonderful things rather than just suck up our Wi-Fi and be vectors for somebody breaking in, hacking into our computers.
Yeah, 100%. And actually, going in that direction, one of the things that we were looking at is okay, it's really cool to deploy models on the cloud that are fast and cheap and on iPhones that like uh, extremely fast. But one thing that we've been doing kind of on the side as a kind of a pet project of one of my employees is putting a model on a Raspberry Pi that you can communicate with just with a microphone, basically. And so he's been able to build a very, very small device that runs on the battery pack, doesn't need connection to the internet. And we think that that's a fairly like versatile, just independent piece of logic that you can start putting into any devices.
Huh.
Yeah.
Wow.
Whether it's an autonomous vehicle or microwave or whatever
Yeah.
you want. Yeah.
Yeah. Yeah. Of course, you deliver a lot of different models, and they're all smaller than perhaps competitors or the models that they're derived from, but they're of varying ranges and varying different levels of power and capability depending on what customers want and need. The the way you do that is tensorization. What does that mean? What does it mean to shrink a model and therefore shrink its compute and energy consumption?
Great. Let me take you through the like standard ways of doing it, and then I'll tell you a little bit about how we do it. So basically, there's two very popular and widespread ways of compressing AI models in general, and both of them are destructive. The first one is called quantization. So in it, you have trainable weights, and each weight is encoded to several bits. Like say 32 bits, for instance. And one way to make those models smaller is to say, okay, I'm not going to encode it to 32 bits anymore. I'm going to encode it to 8 bits. So I'm basically, if my weight is a number between 0 and 1, I'm just like shrinking the space of values it can take.
From a human perspective, if your neuron is connected to 100 others, no, sorry, now you're connected to 8.
For instance. Yeah. Actually, it's interesting you would say that. That is closer to the second method.
Okay, good.
How about this? Okay, I'll try to roll with your analogy. Okay, if two neurons are connected and if they can exchange a certain complexity of information, like for instance, okay, how about this? Two neurons are connected. One of them says to the other, this is a strawberry, this is a cat, this is a dog, this is a microwave. And then I'm like simplifying the information that can be transmitted. And so I'm only saying this is a strawberry or this is a microwave.
Yeah, two options.
And pruning is the other technique where one neuron is connected to 20 other neurons. I'm going to say, actually, these connections don't contribute very much. So I'm going to discard a bunch of them, and now it's only connected to 2 neurons. So yeah, the two standard ways of making AI smaller. On the one hand, you make connections simpler. On the other hand, you just get rid of a bunch of connections.
Cool. And which do you?
So, Nina, what we do is kind of a generalization of the second one. So we discard weights.
Yeah.
But before we do that, we're going to reorganize the information so that we focus all of the information on certain connections. Then that allows us to discard connections in a much less destructive way. So we're still destructive, but we have much finer control over how destructive we are and like
You're intelligently destructive.
Exactly. Yeah. Oh, I love that. Intelligently destructive.
Awesome. Very cool. It's really interesting because I think it was literally this morning, could have been yesterday, there was a model that got released, I think in Montreal by a researcher. I think she works for Salesforce or Google or some, I forget who, but she released something that's very cool and it's tiny, but all it does is a certain type of reasoning, right? So a lot of people who shrink models, they focus on certain types of tasks, maybe playing game, or maybe this one has some language capability or something like that. Is that what you do? Or do you try and still build a model that has general applicability, but is just smaller?
So yes to both. How do I answer this? I think one of the things that we've learned through the whole like large language model, like the past few years, basically, the past very recent artificial intelligence history, is that models are capable of doing an awful lot of things really, really well. And it's actually, in a lot of cases, it's actually more interesting to have a generic model than very, very specified models, because that opens a lot of doors without actually having that much of an extra cost.
Super interesting.
What we do is, first and foremost, we create these compressed models, but they're still like general purpose. And then if we want to go beyond that, we apply some fine tuning and we increase performance in certain areas. That's
Cool.
a huge part of our value proposition. On the side, we have also started doing what you're speaking about, which is to say, okay, model, let's get you to forget everything about diagnosing cancer, and now you only know about microwaves, basically. And
That's your model for a microwave right there. Doesn't need to know how to cure cancer, just needs to know how to make popcorn or whatever.
Precisely. Cool. And that's difficult to do because these are highly complex, very black box models. But it's true that in doing this, this is one of the very, very simple ways that we can make models a lot smaller. Basically.
Super, super, super interesting. Now, you've got a quantum computing background, and your company has a quantum computing background, and there's some talk that this is quantum inspired. Talk about that. What's that mean?
Great. Yeah, so we started out in quantum computing, applied to industrial use cases years ago. And we were kind of doing two things at the same time. One of them were these very visionary long term algorithms to run on physical quantum computers. And the other one was a quantum inspired offering, which was basically it runs on GPUs and it takes ideas that come directly from quantum computing and simulating the quantum world. And in lots of cases, we saw that this allows us to run certain hard problems, especially in AI, much faster. We started focusing more and more on that part of our AI story. And then when large language models came about, and we realized that we really had something that was incredibly applicable to that, then we really started focusing more and more on that part of our business. We still do quantum. It's still part of our story. We still have the vision of porting everything to quantum computers in future, but that's our long-term mission.
But that'd be crazy. Large language models, small language models, and quantum computers. I didn't even know what that would look like.
We're very excited. It's not for today, but I'll definitely let you know when we do it.
Very, very,
I'd like
very
to give
cool.
you a little bit of insight of how quantum fits with this idea of compressing AI, basically. The the idea is that the quantum world is extremely complex and you need a lot of computational power to describe it. But quantum researchers have realized that there's a family of extremely potent algorithms, these tensor networks, that allows us to identify what are the relevant pieces of the quantum universe, basically, and just focus on describing those.
Ah,
That's very similar to what we're doing for large language models. We're identifying, okay, what are the relevant pieces? And now let's only keep that and get rid of all the rest.
super cool. Super cool. Now, apply this to your everyday person who's using ChatGPT or Claude or whatever, Perplexity on a daily basis. I mean, obviously those systems, and OpenAI got in trouble for it a little bit when they came out with 5, and then we're going to select a model and stuff like that. We'll select maybe a more efficient model. Maybe it's a worse answer, but it's still pretty good. So they're working on their side of it. But is that something that we should think about as consumers of AI? Wow, I'm using a lot of electricity, or I have a big carbon footprint, or whatever it might be. Is there something more efficient I should do?
Absolutely. I mean, I think as consumers, we're all responsible for our usage, right? Yeah, I think small language models do hold a part of the answer here. Obviously, small language models doesn't suddenly mean that all AI use is responsible use, but it does mean that we're making better use of the resources we have, basically.
Mm-hmm.
So
Mm-hmm.
that's a part of the reason why we've built our technology is let's allow a data center to serve call it 20,000 people instead of 10,000 people. I'm just making up numbers, but
Mm-hmm.
you
Mm-hmm.
get the idea. I think it's also important to point out that people often focus on the costs of training AI,
Mm-hmm.
but the cost of using AI is very much comparable, basically,
Mm-hmm.
on the scale of the planet. And there were statistics about this where it was assumed that every I don't know if you remember, there was a fad at one point of people generating their images as a little plastic toy, and each of these
Yes.
cost
Yes.
thousands of liters of water, and were equivalent to running a light bulb for hours.
Yeah. Yeah. Yeah.
But
Huh.
I think where technology is important as well, or where small language models are important as well, is also has to do with the direction that AI is naturally going in. At the moment, like AI is heavily cloud dominated.
Mm-hmm.
And therefore, every time I want to do a query, I'm calling up some server in North
Mm-hmm.
Virginia that's running my calculation. And obviously, that's extremely like energy intensive. I
Super
believe,
laggy.
yeah, and super. Yeah, absolutely. I believe that very, very naturally, there's going to be a commercial pressure to push those computations quite rapidly onto the end user. So have our computers, our devices just simply ship with dedicated models, basically.
Mm-hmm.
And then when I ask for a run, when I say like, hey, can you generate an image of my face on a McDonald's
Mm-hmm.
box or something,
Mm-hmm. Mm-hmm.
um, for the computer to make an educated choice of like, is this a run for the cloud or is it a run for my
Yeah.
machine, basically?
Yeah, that's absolutely huge. It's huge. I mean, Apple's doing some of that stuff. They've got some AI cores on their iPhones and stuff like that. I'm sure Google, Android is working on some of that, and Samsung and others and like that. But a huge place for that is robotics. I was just talking to Starship. They do the most robotic deliveries of anybody on the planet, 9 million so far. It's a little six-wheeled thing that goes around a city, goes around a campus and delivers stuff door to door type of thing. And that thing, I mean, it doesn't use GPS. It's not effective in a city. Sometimes you under a tree, under a building, whatever, and it has all the intelligence it needs, but maybe it gives a little bit more, and maybe a small language model would help. Humanoid robotics, we're already talking about that. What kind of hardware they need? Because you know what? When you come up across a humanoid in the workplace, and you want to work together, you don't want to ask the robot a question and it thinks, it captures the audio, sends that somewhere in the cloud, transfers that to text, asks what that means, asks what it should do, and 5 seconds later you get a response, right? I mean, you want to have a communication like you and I have where it's relatively instantaneous, right? And so having that ability right on the edge right there is absolutely huge in all
Oh,
kinds of different
absolutely.
robots.
And there's certain cases where if for instance you have an engaging car, you can't just suddenly not communicate with your car anymore because you're not connected to the cloud because you're in in a tunnel or something. You know?
Yeah.
Like
Yeah.
there's some situations where you have to rely on the edge. There's just no other way. Right?
Mm-hmm. Mm-hmm. Super cool stuff. Thank you so much for taking this time. Super interesting. Looking forward to learning more as you continue to develop.
Amazing. Thanks so much for the opportunity.